Thank you for your love and kindness that's happening right now. Thank you for your care, and for your blessing. Amazing, amazing blessing, Lord. Thank you. Father, I pray your blessing on Nathaniel Taylor as he's at the funeral of his grandfather. Father, I don't know how connected he was, but either way, you can not only enrich him, but you can make him a blessing there. You can make him a blessing to his family. You can make a real blessing to those around. I pray you would do that. Father, you just open the doors, help him to see him, and minister. And you can minister grace to his heart as well. In fact, that's what you promised to do. Comfort us in a way that we can't be comforted any other way, so that we can comfort others. And so do that for him, Father. I pray you would. And thank you for this class, and for what you have for us here today. In Jesus' name, amen.
Amen.
Okay. So little time and so much to do. I graded your tests, so I've got them all. And what I have, let me see. So what I've done in grading number 4, the media 4 that you did. So what I have here on these little pieces of paper are your scores. Your total scores at the end. The scores for section 1 is in the first. For section 2 is the second. Section 3 and 4 are combined. And I will tell you what, I will show you what they mean.
Are you saying for the test or the media review?
Media review, this is media review.
I was gonna say, we don't have to do that.
So these are the ones that, and I asked another student that's not in this class, that doesn't have a dog in the race, to somebody has 2, I think. No, it is 2. Okay. So I had a problem, or I had an issue with one that I was concerned about. A couple people completely misinterpreted the first 2 questions. Like, and a couple of you, I'm not sure how, the 2 of them completely misunderstood. So what is, so you have part 1, first part 1 is 40 points. Part 2 is 35 points. Part 3 and 4 is 50 points. And then your total. The total score out of 125. Okay. So, because I didn't want to charge foolishly, the ones that missed, so this is on your little piece of paper, you'll see a number here, and then a number after your name, you'll see a number here, number here, number here, and then the total. So total on this one is 125. That's the total number of points you could get. So 50 points for these 2, 35 here, 40 for here. So I'm not going to do anything about these. These are pretty straightforward. You got them or you didn't. At least my sense was. But this one and this one. So this one was worth 40 points and this was 35. So what, after asking a student what he would do in a case like this, where I didn't want to disadvantage somebody that from looking at their last part understood what I was asking, but didn't understand the first part. So they answered differently than I would have thought. So this is the question. This is media four. So I said, blah, blah, blah. And then I added to. I added to a little bit. What evidences did the scientists discover? Now, I didn't have that word. That was right there. Discover. So they uncovered it. They had to look for it. So they weren't looking at the West Coast. They weren't looking, that part of the video that talked about the West Coast being in danger, because you have the same scenario. You have subduction happening on the West Coast. Juan de Fuca Plate is subducting under the Northern American plate. So they've been doing that since 17 something. So this says it was about 200 years. In the West Coast, it's been more than 200 years. So and tension builds up. Some of you knew that tension builds up. This plate up here is being pushed like this, and this is going down, and it's pushing it, and it's pushing it. And one day, like this thing, it would go, whing, and then there'd be a tsunami. Like there was in Indonesia in 2004. That's what happened. So, what evidence does the science discover to support the idea that what they were looking at, and what were they looking at? They were looking at the Indonesian earthquake and tsunami. They were there. They took that big boat. And it is pretty amazing. I mean, I don't like all the hype around it's a docudrama, so they want you to go, oh, it's going to happen now. Well, but the science in it was good, and how they looked for it was really excellent. I mean, they looked at something that looked like it was it. Oh man, mountain slide, this has to be it. The big mountain slide, big thing at the bottom. Oh man, 8 miles down, it's got to be it. It wasn't it. If you said it was, you were wrong. Because that wasn't it. They looked at that and they thought it was, but then they find a plant that was about 10 years old growing on that thing, and they say, well, it couldn't be. And they found a bunch of mud on it that if it had been recent, wouldn't have that much mud on it. So 2 reasons they said we wanted it to be, we thought it was, but then it wasn't. So they continued on, and they dove again. And then when they saw that coral that had been lifted up, somebody measured it, and so they looked down there, well, that was where it was. So, what I'm giving you an option for, I should probably tell you that. You don't have to do it. If your score on this thing was fine with you, that's fine with me. But if it wasn't, if you missed this question significantly, this was worth 40 points. So if you missed that one, or you missed this one, what specific tectonic plate movement information in scientific language? If you said, and the plate was subducting, and then ping. Well, I know what you mean. But this ping is called what, anybody?
Elastic rebound.
Elastic rebound. So, 2 plates. Oceanic plate, subducting under a continental plate. Friction happens. One flips up, elastic rebound, which caused what we read about happen. So I wanted more scientific language. Very few of you moved that way. I tried to accommodate. I know what you're saying, and so I tried to give you points based on what I understood you were saying. But so these 2 questions. If you want to make an adjustment in your score on these 2, this is set. You got that. You got what you got. But these 2, you can. You don't have to. It's no requirement. There's no requirement to do that. For those that want to, you can see me after class. I'll actually, I just put these, pass these out to you. I'll put these are just the 2 questions. You answer those 2 questions and turn them into me next Monday. Okay?
Mr. Nelson?
Yes?
Are you gonna be passing back our media review 4 so we can look and see if we
No.
missed it or not?
Well, you can see by this. By the little thing I passed out.
Okay,
If you see your points. If you got 10 points on this one,
right,
that says you missed it. So if you got 35 points on this, that says if you want to redo it, the most you can get is 5 points, max.
but the last one's between 2 of them, so how would we know?
You
how
don't,
many?
the last ones are set. Those are fixed. There's no changing those 2.
Oh, these are for each question?
Yeah, question 1, question
Okay,
2,
okay.
question 3 and 4.
Okay,
Question 3 and 4 is set.
okay, thank you.
Whatever you got on question 3 and 4, that's what you got. I'm not changing that. I thought that was obvious enough. And it was just a matter of your knowing what was. Now, what I did on 3 and 4, I did combine the 2 in my brain. Because some of you answered in number 4 what should have been in number 3. So you didn't lose anything for that, because I gave different points for those. So I would give you the points for it. If you answered something in part 4 that should have been in part 3, you got more points for it in 3, well, I gave them more points. So I looked at 3 and 4 together. So that's how I looked at it. So if you want to redo problem 1 and 2, you can do 1, or you can do both, or you can do neither. And your total score is at the end. Whatever you got out of 125. If you got a lot out of 125, I didn't know that I would bother. I don't know that it would be important enough to bother. And you can divide, this is not math, but, so, if you got a 95, and you take out your calculator, and you divide that, 125 into 95, that will equal your percent. Okay? It'll either it'll give you a decimal point, so a decimal point here, you get a percentage, and then you move the decimal point over 2 clicks, and that's what your score would be, percentage-wise. So if you want to do that, so do you understand what I'm doing? I'm giving those that made a mistake on what they did a shot to redo it. But it'll be due Monday, class time. Okay, and I'd rather you not confer with somebody else. So I'm not gonna be able to hand these back to you. I have them all graded, but I don't wanna hand them back until people that, when the exercise is up, if nobody does, then I'll hand them back probably next time. Okay? Everybody clear on that?
And we're able to just handwrite on those papers? Or do you want us to retype?
No, you don't have to do problem 3 and 4, only those 2. If you want to do one of them, just type out the one. I just want to see when you're doing.
Okay.
Okay. So you could write number 2. You could put 2 down there when you wouldn't have to write everything that I've written there. Okay. Just put your name on it. Tell me what problem you're going to redo, and then I will reevaluate that one. And on Monday, then if you didn't turn one in, if you turned in one to me and I didn't turn it back to you, then you need to see me and I need to look around my house. But as far as I know, I turned back all the ones that I had graded and all the ones that I had in the grading stack that were there to do so. Okay. Okay. Now, because, okay, that's this. Okay, I'm gonna pass it. I'm gonna go over your test, but I'm gonna cover this first. So these are the first 2 sections because I don't think I have the time to do what I've always done in this class. Typically, these would be given and you would have to fill them out. But you are not gonna have to fill them out. Did you? Oh, okay. I'll try to get it corrected and let you know how that is. So, this, normally, I would have this and I'd go over it, and I'm going to go over it, but I don't know if I'm gonna have time, because if I return your tests and I say anything about that, which I'd like to, light and wavelength hand down. Okay. So you have, oh, no. What am I doing? Yeah, I don't know. Had a great weekend, but it left my mind boggled. Here. Okay, this is this left section on light, and then we have a second section, and I'll see where we are when we go through these two. And then, so, that's a passage of scripture. See to it that no one takes you captive through hollow and deceptive philosophy, which depends on human tradition and the basic principles of this world, rather than on Christ. Colossians 2:8. We're not going to watch this right now, but if we have time, we'll do that. So light, this is light. I like it. I like this subject. I like light. I like colors. It's just, most people like light. If you've lived in Alaska. So have you ever had any problem with the dark that goes on? No?
I like it when it's dark.
Well, most of the people that I know that have gone up there to live that hadn't lived there before have struggled. Some more than others. Struggled with it being dark. For so long. No. I mean, it doesn't have an effect. There's a place down on the West Coast that is a rainforest, the whole rainforest, which is, you can walk in 10 feet and it's not dark like night, but it's thick and dank and heavy. The suicide rate there, people living in that area, is really high. My uncle lived there for a while. He couldn't stand it. So it does affect, the darkness does affect the people differently. But light, as far as we know, and we don't know all about this subject, we don't know, there's a lot we don't know about it, but it has both a particle and wave properties. Now, why I've done this blue stuff for you and hand this out is to keep you tracking, for one, but also some of this stuff is important. So light sometimes behaves in like invisible particles called photons, little thing, pooh, and photons can collide with other particles. That's why we get scattering. That's why the sky is blue. And that's why the sunsets are red and orange and yellow. Because light has been scattered. The wavelength of these particles, because they're all different. Reds are longer wavelengths than violets. So, I could digress, but at the same time, light also displays wavelengths which can act similar to water or waves or sound waves, water waves. Light, in other words, has a dual nature. And they don't know, there's still, everything I've seen, you can watch current stuff, right up to date stuff, and it's still a mystery how these things operate. The creator of them was pretty clever. Light waves also possess energy and momentum. We observe their ability to heat matter. Not just visible light, but the range of light, and we'll get to that coming up. So the speed of light, 186,286 miles per second in space, which is in a vacuum. It slows down a little bit when it's not in a vacuum. This is roughly 5.8 trillion miles a year. So when you talk about a light year, like the distance between a star and us, and you talk about a light year, one light year is 5.8 trillion miles. That's one. And when you talk about these stars being hundreds of light years away, and when you look up at the sky and you see Orion, if you know where Orion, that's the one I know. I know Orion, I know the Dipper, but I don't know a lot of the others. But Orion has a couple of stars. It has in the ends, the hands and the feet. And the feet stars are a couple hundred light years difference in distance from us. A couple hundred of these things. That's a long difference. But one is brighter than the other. And sometimes the one that's brighter is farther away because it's bigger and really brighter. But they all look like they're about in the same place if you're looking from here. They're all little bright and twinkly guys. So anyway, the nearest star to Earth, other than our sun, is Alpha Centauri C, which is about 4.24 light years away, which is 24.6 trillion miles. This is a long way. I love to drive, but I wouldn't want to do that one. I just would, I mean, it'd be, well, if it was so pretty, I wouldn't live long enough though. So the Earth, Earth 7, that's 7 times each second, or 671 million miles per hour. So this speed of light, it goes around. It moves really fast. So what did that say? Why is that? Yeah. 186,000 miles per second would translate to traveling around the Earth 7 times each second. So it's not 7 times, but it's 7 times a second and go 671 million miles per hour. Light travels slower when not in a vacuum. Space is a vacuum. Light also radiates outward from a source uniformly in all directions. It goes out. Like if you have a flashlight, you shine a flashlight in a dark place, it illuminates what's close. But if you hold it up and get farther away, you'll see that it fades and it fades as it goes. So it does that. And that's intensity. The intensity, the amount of light per unit area, number of photons, say, decreases as the square of the distance to the source increases. So this is known as the inverse square law, which means just like this. If you had 36 photons right at the beginning, right here, 36 photons, and 1 meter away from the source, say I was the source, I had 36 photons, and I said, go boys, and so they all went. So 36 photons are going out like this. And so 1 meter away, this would be 36 photons per meter. So a meter is, what, 39 inches? So there'd be 36 photons for that meter. They go out, they just go out uniformly. Boom. But if they're 2 meters away, this is 1 squared, 2 meters would be 36 divided by 4, which is 9 photons a meter. And 3 meters away, so 9 plus feet away, they'd be 3 squared is 9 and 36 is 4, so there's 4 photons per meter, which means the light you get a meter away is 36 of them per meter. you go another meter, it reduces to 9 photons. So you don't get as intense light there far away, and it keeps reducing the farther away it goes. It means the farther away light travels from its source, whatever source that is, the less energy, less heat, less brightness it has. So it reduces in energy, heat, and brightness. So you find that in the summer, when the sun is closer to directly overhead, it's not directly overhead here, but it's closer to it, June 21st and 22nd, the summer solstice, the sun is directly overhead at 23.5 degrees latitude. So from the equator, you travel up, in our summer here, you travel up 33.5 degrees, and it reaches that point, June 22nd, 21st, 22nd. The sun goes. And after that, it starts going back down. It goes the other way. And when it's 23.5 degrees up here, it's the opposite in the southern hemisphere. So down where you're living, it's going away from you in the summer. In our summer, 23, you're below the equator, right?
Cheers.
You're not? Yeah, you.
I mean,
Yeah, us, yeah.
mhm.
You're below the equator. The equator's here and you're down here, aren't you? Yeah, so, but it would go up to 23.5 degrees. That's the farthest it goes. And then it starts clicking back and goes back in our winter solstice, what we would call the winter solstice. It would be 23.5 degrees on the other side of the equator. And if you notice that in the winter, the sun just seems weaker. It may be out there, but it isn't as intense. It can be a sunny day, but it's not intense. Because the sun is not closer to overhead. Now in the equator, it's overhead. And it's close to overhead. I mean, that's why the equator is warmer overall. And it doesn't vary so much because you've got the sun that is going from 23.5 degrees to there, and it's going back and forth in that same. And that's why in the far north, in the winter solstice, there's a part where they don't get any light, and then in the summer they get light 24 hours. So that's what the solstice does. So the sun does that. It's not as intense as sun is. So wavelength. So now we go to the second page. I think I gave you 2 pages. Yeah. And okay, so wavelength number 1. The only physical difference between radio waves and light waves is their length. So looking at light as a wave, you've got the wavelength is from crest to crest, or trough to trough. That portion and that portion, that's a wavelength. Radio waves have lengths as great as 6 miles or longer. You have some waves, the difference between that wavelength, crest to crest or trough to trough, is as much as 6 miles. And then the other extreme, you have gamma rays produced by disintegrating atoms. Radioactive elements have a wavelength of less than 4 billionths of an inch. You got an inch and you take 4 billionths of that inch. It's little tiny. It's little tiny. So those are gamma rays. So just for you knowing, so the distance between the crests and troughs, if they're 4 billionths of an inch, that stuff will penetrate your body. That's why with X-rays aren't this small. X-rays are a little larger. But that's why they put stuff on you when they do an X-ray thing, so your whole body isn't getting bombarded by X-rays, because X-rays can do damage to your body internally. Gamma rays can do bad damage to your body. because there's nothing to stop, they go right in. So if you ever hear a gamma wave warning, then take heed. So the visible light waves are a very small group near the middle of the spectrum. Boy, oh boy, you should know that. The middle of the spectrum with wavelengths ranging from 16 to 28 millionths of an inch. 16 to 28 millionths of an inch. It's still really small. But that's where they're near to the middle. That's what you want to know. That's the visible. That's what we see with our eyes. Wavelength is emitted within the narrow range of visible light. Each individual wavelength is emitted by the sun, but greenish wavelengths are emitted in greater intensity than are others. This mixture, however, enters the brain as white. So these are wavelengths. They're not to scale, obviously. I mean, it looked like you wouldn't be able to see the ups and downs of these things if it was scale. But so violet, the wavelength, it has shorter wavelength. You can see that. And then purple, and then blue, and green, yellow, orange, and red. So green is like this. The green tends to be, there are particles, particulate matter in the air, that tend to absorb and scatter wavelengths. And why we see a sunset the way it is because this stuff in here is scattered, particularly blue, and that's why we have a blue sky, because this stuff is being scattered all over the place. But this stuff is too long to be affected until you get it going through atmosphere, a lot of atmosphere. So incandescent bulbs emit a range of wavelengths like the sun does. That's where it created to be light in a room. But because of what you use, the tungsten heating up, it doesn't get the same, it doesn't heat up like the sun does. So you don't get the same wavelengths. So they're cooler. So wavelength balance is dependent on temperature. Sun superhot temperatures cannot be matched by incandescent filaments, so they're not able to produce as many short wavelengths as the sun. So they end up producing the longer ones. And for one of these things, for fluorescent tube, and I don't know about these, but the fluorescent anyway has a coating on the inside, and they pass electrical current through that, and it's diffused as it goes through that stuff they put on it. It's not so important. Three major characteristics of light waves concerned to a photographer. If you're taking photography, that's what, well, you'll see why. Intensity determines the brightness of the light. The wavelength, which depends on the distance between crests and largely determines color. And its polarization, the angle orientation of the crest. All three characteristics are influenced by what happens when light waves interact with ordinary substances like air, metal, glass surfaces, tiles, etc. Now this, you don't have this. And I don't know. I didn't get to. I have it. I tell you, I'll either pass it on next time or I'll post this stuff. Because this is important to understand. So, what's generally the shorter wavelength radiant energy that does damage to the human tissues, like X-rays, gamma rays, ultraviolet rays. Why? Because they move faster. They're at higher frequency and can penetrate the objects more deeply. So they're higher frequency. The wavelength are closer together, much closer. And they happen to be able to damage human tissue. They don't damage everything, but they do human tissue, X-rays, gamma rays, and ultraviolet rays. So they're, just because they're higher frequency. And frequency is the number of waves that pass by one point in 1 second. So there's 1 second, and the frequency is the time that the number of waves here that pass through. So they can count from here, they can count from here, they can count from here, but the number of places from here to here, from here to here, from here to here, that's what they're talking about, the wavelength passing. And crest, trough, and amplitude is the distance from a baseline up here. The height of the waves is the amplitude and the distances, etc. Frequency and wavelength are inversely proportional. So the shorter the wavelength, the higher the frequency. So you got, if the wavelength is shorter, if the wavelength is shorter, the shorter this is, the higher the frequency. So gamma rays, like are, whatever it is, 4 billionths of an inch. And radio waves are 6 miles. So you'd have 6 miles between here. They're not close together. Radio waves aren't going to do you any damage. But the closer these are together, the higher the frequency. Because frequency is the number of waves that pass by in 1 point in 1 second. So if these are closer together, more are going to pass by. Longer wavelength, lower frequency. Visible light is only a very small part of the spectrum, as I said before. Visible light is radiant electromagnetic energy that can be detected by the human eye. This whole thing, that's why my idea of when God said, let there be light, what he did was create this electromagnetic spectrum that goes from gamma rays to radio waves. They're all waves, but the ones that we pick up, the visible ones, are the ones that we see, but he created the whole thing. He didn't have to create radio waves. When he said light has to include what we know is that small section, but it all includes everything else. We just don't see it. All radiant energy travels through the vacuum of space at the same rate of speed in vacuum of space. That's you should probably know that in a vacuum of space, it goes at 186,000 miles per second. An understanding of the nature of light is basic to modern astronomy. That's important to remember. See, I have that. That's important to remember. So you should do that. I mean, well, you can do it if you want to, I guess. The vast majority of our information about the universe is obtained by the study of light. We can tell what chemicals a star radiates by light, because they all have a different light sequence. All the chemicals under certain, either going through a cloud of heated gas or coming out, react differently, but they have a different color. It's like a thumbprint. Gamma rays, X-ray rays, ultraviolet rays, etc., and radio waves all being examined in hopes of revealing the light about our universe. It's interesting that at the very beginning God said, "Let there be light." Yeah, so I already talked about that. So you don't have anything about this, and you won't get. I just wanted to say that with photography, what you'd like to get with these flashes is something that duplicates the sun, because that's the usually. Now, you can do creative stuff, so you don't, but a lot of times that's why they started using flash, because if they couldn't take something outdoor, they wanted to simulate outdoor, the light that you get outdoor. So, have you ever heard of limelight? Anybody? Limelight. So limelight, it's usually used in reference to somebody wanting the limelight, which is the center of attention. In the 19th century and early 1800s, those working in acting profession were benefited by mirror reflection of an intensely flaming jet of oxygen and hydrogen gases, heating a disc of lime to brilliant incandescent. So it was referred to on-stage illumination. So you'd have this, you'd be burning this stuff, and it'd send off incredible light, but it was also, as you could imagine, in the 19th century, using a flaming jet of oxygen and hydrogen gases and heating a disc. It was probably a pretty dangerous thing to have, and buildings burned and people got burned. They're serious. So in the 1850s, the discovery that burning magnesium wire produced an extremely bright light similar to daylight. So photographers used it, but the thick white clouds of smoke produced by this method allowed the user the liberty of only 1 or 2 shots before they would have to chokingly flee for air. I mean, you see the old time and they go, poof. Well, that happened. I mean, that's what they were doing. And the following was flash powder, an explosive mixture of finely ground magnesium, potassium chloride, and antimony sulfide, which proved effective but really dangerous. I mean, explode. So if you had too much in there, you'd get hurt. In fact, people were blinded and burned by that. Wherever it was used, there was always a threat of fire. Many photographers and their assistants were burned and blinded. So, I don't know if you are a Superman buff, but you know, he didn't like Krypton. You know, Superman, Krypton was bad for him. Well, that's why he was a reporter and not a cameraman, because they had Krypton in the little flash. So that's just so you know. So if somebody stops, I'm going to stop there. So that was good. If, Henry, could you pass this out while I talk here? This is, please, thank you. Now, for your test, because I'm going to go over your test. For your test, after grading these tests, I made a decision to increase scores universally. Try to be very particular about that, about being equitable among the whole lot of the class. So if I do it to 1, then I do it to all. So I thought, just to take into account my own human frailty and evaluating a question, so I added 10 points to everybody's test. So I know you took it when there was a lot going on, but that's kind of what life does.